Hey everyone, today we're here to look at section 12.1. We're in our last chapter here in AP Statistics, and this last chapter has to do with some other odds and ends for hypothesis tests and confidence intervals. And as it happens, we're going to be looking at the confidence interval and a hypothesis test for the slope of the regression line. Do you remember regression? Well, let's come back to it and check it out. So here we have the question, do students who sit in the front row do better than students who sit further away? Now, I know probably you've heard somebody say that you should sit in the front of the classroom because you'll do better. So this is an attempt to try to add some statistical reasoning behind that. Does this actually work? So what we have here are a set of students. I believe this is 30 students. We got some students in row 1, some students in row 2. We've got some students in row 3, some students in row 4, and some students in row 5, that coveted last row of seating. We also have the test scores that these students had on a recent test. It doesn't say which test. So just as a review, is this an observational study or an experiment, and why? The answer here is a big fat, well, it depends. Did we have assigned seating? Well, if yes, well then this is an experiment because we had the opportunity to assign treatments to our experimental units. So the treatment in this case would be, which row are you sitting in? So treatment group 1 would be row 1, treatment group 2, row 2, etc., etc. But what if it was open seating? What if students just picked their own row? Then, of course, if it's not assigned seats, then this is just an observational study because we only made observations. We didn't make an attempt to assign treatments. So that takes care of our number 1. How about number 2? Why is it important to randomly assign students to seats rather than letting students choose his or her own seat? So this is really similar, or really kind of dovetails into that question 1, because what does it mean if we get a chance to have an experiment? This has everything to do with the fact that we have an experiment if we assign the seats. And if we assign seats, then this experiment can help determine a cause and effect relationship between row and test score. Number 3 are how many random variables, or sorry, not random variables, but how many variables are we measuring? Well, just 2. They are the row and they are the score. They are both quantitative variables because, well, just take a look. The row is a number, and the number has meaning, of course. And the score is a number, and that number has a meaning behind it. So they're both quantitative. Explanatory variable, which one do we think is the cause part of the cause and effect relationship? Hopefully we're saying that the explanatory variable is row, which means that the response variable is test score. Now, next we're supposed to use Staplet to make a scatter plot, and I don't want to make too much of a fuss about this. We could definitely go into Staplet and do that, but let's just take a look at what the scatter plot looks like. It looks like this. Here in row 1, we have the test scores up here. Row 2, we have the test scores over here, slightly lower, actually pretty consistently lower. Row 3, we have one test score that's lower, but kind of the rest of them are a little bit higher than we would expect. Row 4, we're kind of all over the place. And row 5, most of these are lower, except for this one right up here. You'll notice that up over here, we've really got a few points, a few pieces of data that don't really go along with our generally downward relationship or negative relationship. Staplet can also output for us the correlation. It's negative 0.161. Remember, a negative correlation means that the slope of the linear relationship is negative, and we said that already. The equation over here is 84.45 minus 1.15x. I would prefer that you write that as predicted score equals 84.45 minus 1.15 times the rho. What is the slope of this regression line? That slope is negative 1.15. How about we interpret that in the context of the problem? Here's our sentence starter. For every increase of 1 unit in the explanatory variable in context, well, the unit is rho, and the explanatory variable. So for every increase of 1 rho, maybe we should just say from the front of the room, the response variable in context. Okay, that's pretty easy. That's the test score, and we have a negative slope, so decreases by about 1.15 points. Remember, you don't have to reinvent the wheel. We have these sentence starters for almost all of our interpretations. You just have to make sure that you have them up in the old brain so you can write them down on call. That's the bad news for you. Okay, so this first page is pretty much a review of, I think it's chapter 3. Let's take a look at some new stuff. Now, does the negative slope provide convincing evidence that sitting closer causes higher achievement? Or is it plausible that the association is purely by chance because of random assignment? And let's face it, that could be the case here. Maybe we just happened to sort a lot of, or assign a lot of the higher scoring students to the front of the room, purely by chance. So in order to answer this question, we need to know more about what this means, purely by chance because of random assignment. Now, if we assume that the seat location has no effect, then we could just randomly assign all 30 scores to any of the seat locations. And what that sentence is saying is, no matter where, let's say, I scored a 72 on the test, no matter where you sit me, I'm going to score 72 on the test. My row number does not affect my test score at all. Okay. Well, if that's true, then if we just sort the students into different rows, then that shouldn't change things. And I want you to take a good look at this sentence, or this part of the sentence. If we assume that the seat location has no effect on the exam score, that sounds an awful lot like a null hypothesis to me. So let's see. What we're going to do is we're going to write down each of those 30 exam scores on an index card, shuffle the cards, and then randomly assign to seats. Like we said, if there was no, or if the row number doesn't affect the seat, then if we just randomly put everybody on a seat, we should get a slope which is not too far off of what we saw. Now, naturally, like we always do, we can't really do this because we're virtual. So here's what we did. My trusty Google Sheet. Over on the far left, we have the original seats and their scores already put into a chart. We have the slope is negative 1.5. I had to round that. We'll talk about that in a second. And what we're going to do is we're going to take those scores, and I have them here, but I have them shuffled. I'm going to shuffle them again for you. So I'm just going to select that range, and I'm going to randomize it. And that's going to give me a new slope. So this new slope here is 2.6. So let's do a little bit of, well, yeah, let's take it, let's put that into our chart, 2.6. Okay, and then we're going to take a second shuffle here, and we're going to figure out exactly what slope we would get if we were to shuffle the deck again. Again, we're randomly putting students in different seats. Well, this time we got a slope of 0.7. We're going to do this one more time. Shuffle number 3. We're just going to take all the scores and we're going to randomize them. And it looks like now we've got a slope of negative 0.4. Let's put this over here, negative 0.4. And then we're going to put this in our chart. Well, so what? Okay, well, here's what's what. We did this 27 more times. So we have a total of 30 different observations. And we created this dot plot based on those 30 observations. Look at this dot plot. Single peak, not quite symmetric, but definitely close enough for us to say, hey, maybe this is a normal distribution here. That's important to us, okay? Because, as you might guess, this is a sampling distribution, or at least it's part of a sampling distribution. 30 observations out of all the possible different ways that we could mix all the students. There's definitely a lot of ways that you can mix 30 students into a seating chart. So this is just a start of a sampling distribution, but even if it's just the start of a sampling distribution, isn't that remarkably approximately normal? Well, I'll let you think about that. Back on our chart here, I'm not going to bother writing down all the scores. If you were doing this in class, I would have you do that, but that's not as important here. Here are the different slopes, and here is our dot plot. So now you have calculated 3 different possible values for slope based on random assignment. Take these 3 values to the dot plot on the whiteboard, really here, and when everybody has recorded their data, you're going to copy it below. Here's what it looks like for my fake class, which is just as good as a real class, maybe? I don't know. Let's talk about this dot plot. This is definitely an approximate to the sampling distribution, not just any sampling distribution, the sampling distribution for the true slope, if we assume that the row does not affect the score. That sampling distribution for the true slope is normal if conditions are met. We don't know what conditions at this point, but there are always conditions for an approximately normal distribution. So our slope was negative 1.15. How rare is that? What is that p-value? Well, let's count how many of our points, how many of our observations were 1.15 or less. And that is just, what is that, 5 out of 30? About 0.1667. Why don't we take a minute and let's interpret that p-value. Here is that sentence frame. If H naught in context is true, then there is a p-value probability of a sample size of n having a parameter, in this case, less than our statistic value. So we're going to fill that in. So if rho does not affect test score is true, we don't need is true, there is a 16.7% probability that a sample size 30 has a slope less than negative 1.15. In other words, having a slope of negative 1.15 is not statistically significant if we assume that rho does not affect test score. Okay, so this means that rho does not affect test score. We're going to take a quick look at our important ideas. We've got the slope. We've got parameter, and we've got the statistic, and we've got the interpretation. All of this you'll have to have a good grip on. So the slope, from now on, the statistic we're going to use is B1. And the parameter value, B1, approximates something called beta 1, which would be the true slope of the relationship. Similarly, the y-intercept, the true y-intercept is going to be called, sorry, I said B, I meant beta, beta 0, and for the slope, beta 1. So beta 0 or beta naught is the y-intercept, the true y-intercept of the relationship, and it is approximated with the statistic B naught. The least squares regression line then is given to us by the average of y values, or y, is equal to beta naught minus beta 1 x. Sorry, that chart was kind of driving me crazy. The standard deviation of the residuals, we're going to talk about that quite a bit. And you would imagine that if the linear relationship was a good linear relationship, if it really showed something, then that standard of the deviation of the residuals would be really small. Now we use sigma to be the true standard deviation of the residuals, and we use S to be our approximation of that standard deviation. Also, we have something called the standard deviation of the slope. Again, ideally, the standard deviation of the slope would be small. We call that sigma B1 for the parameter. And for the statistic, we're going to call that either SE subscript B, or we're going to call that SEB. One of those two is usually just fine. So we are very interested in S. We are very interested in SEB. We know that B naught estimates beta naught, and we know B1 estimates beta 1. So let's check out our understanding here. Mrs. Barrett's class did a fun experiment using paper helicopters. After making 70 helicopters with the same template, students randomly assigned 14 helicopters to each of 5 drop heights, 152, 203, etc. Teams of students released the 70 helicopters in a random order and measured the flight times in seconds. The class used a computer software to carry out a least squares regression line analysis for the data, and this is some of the output from the regressional analysis. And it says we checked the conditions for performing an inference earlier, so clearly there are conditions here. Now, a lot of what gets done in Chapter 12 is learning how to read this chart. You must learn how to read this chart. So, letter A, what is the estimate for beta naught? We know beta naught is approximately equal to B naught, and B naught is the constant coefficient. So if we look over here, we've got constant coefficient. That gives me B naught is equal to negative 0.03761. If you will remember from the context, this says that if a helicopter is dropped from 0 centimeters, it's predicted to take negative 0.03 seconds to land. Clearly, this number doesn't really make sense in context. So let's take a look at, for beta 1, what about beta 1? Beta 1 is approximately equal to B1, and we can find B1 in our chart. It's in the second line of the chart next to the explanatory variable. So here, B1 is equal to 0.0057. For every increase of 1 centimeter in drop height, the predicted flight length increases by about 0.0057 seconds. How about the estimate for sigma? Well, sigma is approximately equal to S. And I think we see S right here. There is my S. Sigma is approximately equal to S. Therefore, it's approximately equal to 0.1681. The actual flight time typically varies by about 0.17 seconds from the predicted by the LSRL, or typically varies by 0.17 seconds from the predicted flight time by the LSRL. And lastly, how about what is the standard error B? Going back up to the chart, you can see standard error for B right there in orange underneath standard error coefficient. This time our coefficient is 4, or in the orange one, that's in the drop height, the explanatory variable. So that's our SEB, standard error for B. SEB is equal to 0.0002. Here what we're saying is that if we repeated the random assignment, if we did this experiment many, many times, the slope of the sample SRL would typically vary by about 0.0002 from the true slope. It's a very small number, so that's good. And that kind of takes care of today's lesson. Again, we're just kind of starting by looking at the sampling distribution for the slope of a regression line. When we come back next time, we're going to take a look at a confidence interval for the slope of a regression line. What are plausible values for that slope? So we'll see you next time. Have a good one.